and a phone which requires very tiny amount of voltage by plugging them both into the same supply, 230 volts main supply. I mean, the voltage is too low to run a microwave, so how does it work? And the voltage is too high for our cell phones, so why don't they blow up? The secret is a transformer. So what's a transformer? A transformer is a device that can either step up, which means increase, or step down, which means decrease, step down an AC voltage. Okay, what does that mean? How does it work? Well, at the core, the transformer is basically just two coils kept close to each other. One which is connected to the supply, an AC supply, is called the primary coil, and the other which is connected to some device which we want to run, we'll call that the secondary coil. Now the basic principle is the supply voltage is going to generate an alternating current. So the current will keep fluctuating back and forth, and current passing through a coil will generate a magnetic field. And that magnetic field will also fluctuate because the magnetic field depends solely on the current. And because of that, Mr. Faraday comes and says, changing magnetic flux through a coil, there will be an EMF induced. So an EMF gets induced in the primary. What is also important to understand is that that same magnetic field will also get linked because the second coil is kept very close to the first one. It'll also pass through the secondary. And as a result, as the flux changes over here, as the magnetic field changes over there, the flux also changes in the secondary. And again, an induction takes place in the secondary. And because of that, there will be an EMF generated in the secondary. And as a result, there will be a current generated in the secondary. And that's how the bulb starts glowing. Now at this point, you might say, hold on a second, what a waste of time. Why can't I just directly connect the supply to the bulb? Wouldn't that be just easier? Well, if you do that, then the voltage at the bulb will be exactly the same as the voltage that you are providing over here. And that's not what we want. We want to be able to either increase this voltage or decrease the voltage. And that's the idea behind a transformer, either step it up or step it down. So how do these coils help do that? Well, let's analyze the voltages at the primary and the secondary. To do that, let's start by looking at a single coil over here. We know from Faraday's law that the EMF induced in any coil due to the changes in the flux is given by E. EMF E is the negative rate of change of the magnetic flux. It basically means if the flux changes very fast, then there'll be a higher EMF induced. That's the whole idea behind this. So this is the EMF generated in one coil. Now, if there are total, let's say NP number of coils, where P stands for primary, then what is the total EMF generated? Well, the total EMF generated, that will be the voltage in the primary. That will be just NP times E. NP times E. What about the secondary coil? Well, we can do similar calculation. We can say that through each coil, the EMF generated must be the same. Because the flux here and the flux here must be the same. Now you might say at this point, hold on, wouldn't the flux decrease because we're going farther away? Wouldn't the magnetic field lines go farther away and become weaker? You're right, but there is a way in which we can make sure that the magnetic field lines over here and the magnetic field lines over here have the same strength. And we'll talk a little bit about how that happens a little bit later, how we can make sure of that. But if we assume that the flux here is exactly the same as the flux here at any moment, then the flux through each coil, the EMF through each coil, is going to be E. And from that, we can now figure out what the secondary voltage is going to be. I want you to pause the video at this point and see if you can, using that, figure out a relationship between the primary voltage and secondary voltage. Go ahead, give it a try. All right, if the number of turns in the secondary is, let's call that as NS, where S stands for secondary, then the voltage in the secondary is
by Wikipedia.
Power or wind energy is mostly the use of wind turbines to generate electricity. Power is a popular, sustainable, renewable energy source that has a much smaller impact on the environment than burning fossil fuels. Wind power has been used in sails, windmills, and wind pumps, but today it is mostly used to generate electricity. Farms consist of many individual wind turbines, which are connected to the electric power transmission network. New onshore wind farms are cheaper than new coal or gas plants, but expansion of wind power is being hindered by fossil fuel subsidies. Offshore wind farms have a greater visual impact on the landscape than some other power stations. Onshore wind farms can feed some energy into the grid or provide power to isolated off-grid locations. Offshore wind farms deliver more energy per installed capacity with less fluctuations and have less visual impact. There is less offshore wind power at present and construction and maintenance costs are higher, it is expanding. Wind power currently has a share of about 10% of new installations. Power is variable renewable energy, so power management techniques are used to match supply and demand, such as wind hybrid power systems, hydroelectric power or other dispatchable power sources, excess capacity, geographically distributed turbines, exporting and importing power to neighboring areas, or grid storage. Portion of wind power in a region increases the grid may need to be upgraded. Weather forecasting allows the electric power network to be ready for the predictable variations in production that occur. 2021, wind supplied over 1,800 terawatt-hours of electricity, which was over 6% of world electricity and about 2% of world energy. 100 gigawatts added during 2021, mostly in China and the United States. Global installed wind power capacity exceeded 800 gigawatts. The Paris Agreement goals to limit climate change, analysts say it should expand much faster, by over 1% of electricity generation per year. In the higher northern and southern latitudes have the highest potential for wind power. Installed capacity has reached 650 gigawatts in 2019. In most regions, wind power generation is higher in the winter when PV output is low. Reason, combinations of wind and solar power are recommended. G is the kinetic energy of air in motion, also called wind. Wind energy flowing through an imaginary surface with area A during the time t is. Where rho is the density of air, v is the wind speed, AVT is the volume of air passing through A. AVT rho is therefore the mass m passing through A. 1/2 rho v is the kinetic energy of the moving air per unit volume. Power is a popular, sustainable, renewable energy source that has a much smaller impact on the environment than burning fossil fuels. Wind power has been used in sails, windmills, and wind pumps, but today it is mostly used to generate electricity. Farms consist of many individual wind turbines, which are connected to the electric power transmission network. New onshore wind farms are cheaper than new coal or gas plants, but expansion of wind power is...
In this case are 3 actual voltage transformers, one for each phase. Each has its own conductor in and conductor out. A transformer is a laminated steel core surrounded by 2 different layers of wire windings. One set of windings has fewer loops of wire than the other. The one with fewer loops is the low voltage set of windings. The low voltage windings sit between the core and the high voltage windings. Let's see how it works. The current comes into the transformer through a conductor that joins onto the high voltage windings. This induces a magnetic flux in the iron core. This flux induces a current in the low voltage windings. Because there are fewer complete loops of wire in the second set of windings, the current sent out from them has a lower voltage than the one that came in. To adjust the final voltage further, we can use tap changes. These reduce